Good morning, friends. So far we have developed equations of motion, and we realize that there are distinct advantages in working in the body frame. We all know that if I am using Newton's laws of motion, then I have to work reference to inertial frame of reference. We have found out a way to equivalently work in body frame by applying appropriate additional corrections or terms, so that we still can work in body frame, but we don't violate the condition that Newton's law of motion is valid in reference to inertial frame of reference. And doing that, we found out equation. Just I will write one or two of them. U dot minus VR plus WQ is equal to force, external impressed force, and that is in the x direction, and this is composed of aerodynamic force in x direction, propulsive force in x direction, plus gravitational force in x direction. This I am writing along x direction. What is this x? Please understand, this is the body for our aircraft, and x, y, z, this x, y, z, they are body fixed axis system. What is the implication of that? That although inertial frame of reference, if I write xe, ye and ze, which are inertial frame of reference, their direction is fixed. However, when I am operating in body fixed axis system, as the body rotates, let's say body rotating like this, then the x becomes this, x changes its direction, z becomes this. So there is a change in the direction of x, y, z body fixed axis system. And when I write this equation, what does this mean? It means u dot. What is this u dot? U dot is, in body fixed axis system, u, v, w are the component of total velocity, which is measured with respect to inertial frame, but resolved along body x, y, z axis, right? And since body x, y, z axis is changing its orientation, so naturally u, v, w also go on changing. Just to give an example, suppose this is the airplane, and this is x, this is y, this is z, and let's say relative wind is coming like this. It's relative air velocity. Then you could see that forces along x direction is primarily the drag or the thrust. But if we don't change this and the body changes its orientation, then earlier u was this one, now u will be along x direction, local x, so this will be u. So if I want to write m u dot all this equation, then fx or f aerodynamics x will be the component of this force along this direction. So it will change. How it will change? It will change depending upon what is the orientation of the body fixed x, y, z axis. So I am using the word orientation. Okay, that is important. So we need to know how to define the orientation of the airplane in space. I cannot measure the orientation with respect to body fixed axis, because as the body rotates, axis also rotates. Why axis rotates? Because it is a body fixed axis. So I cannot measure orientation with respect to the body fixed axis. So what is the way out? Way out is we measure the orientation of this body with respect to inertial frame, right? So that is the way we handle the orientation of the axis, or we try to locate the airplane with respect to inertial frame. Okay? And now to understand that, we define something called Euler angles. Euler angles, and we need to know what is the meaning of Euler angle. Typically, you will find Euler angle have three rotations: psi, theta, and phi. Okay, and we will see what is this psi, theta, and phi means. Before we go into Euler angles, two things we need to understand. One is this finite rotation does not behave as vector, that is psi plus theta plus phi need not be equal to psi plus phi plus theta or any other combination. So finite rotation does not behave as a vector. However, small rotation, they do behave as vector. Okay, so these are two things we should keep back of your mind, and it's very easy to see this, that this is indeed true. Okay, now with this understanding, we should go for defining the Euler angles. If I take this as an aircraft, and this is your X earth or inertial frame, Y earth, Z earth, and if this is X body, Y body, Z body, then rotation is the Euler rotation one is the order is important. Order is psi, theta, and phi. Second thing, how do I define psi? Suppose this is the airplane, right? This is the z axis, let's say z of earth. Then psi is rotation about z axis. Okay? Now what has happened? As I rotate psi about z axis, so now the body fixed axis is changed. So earlier this was x, now x is also tilted like this, and y came like this. So theta will be with respect to the rotation about this new y axis, theta. And then now you see the x axis also changes. So phi will be about this axis. Okay? So that is to be kept in mind, and this has been cleared in my last module also, the course on static and dynamic stability. So please remember this, that psi, theta, phi has a particular order. Order is fixed. And second thing, which is also important, I'm just brushing the earlier understanding. Second thing, you should be clear that the standard convention is restricted to a range, restricted to a range minus 180 degree less than phi less than equal to 180 degree, then minus 90 degree less than equal to theta less than equal to 90 degree, and for 0 degree less than equal to psi less than equal to 360 degree. These restrictions you should remember when you are trying to develop flight dynamic model using psi theta phi or Euler angle concept. Okay, and there is a special name given for this psi theta phi, where phi we call bank angle, then theta is called elevation angle, and psi is called azimuth angle. Please understand one thing. Loosely we often tell phi as bank angle, theta as pitch angle, and psi as yaw angle, which is not strictly correct. Why? See the point. What is theta? Theta is not about body axis. Please understand. Theta is not about the final orientation axis, right? Theta is about the intermediate axis. What? So this is the orientation I am starting with. I am giving a psi. Now this becomes y. Okay? Earlier y was like this. Now this becomes y. So theta is about this y axis. Okay? Similarly phi will be about this axis. Okay? So they are different compared to the concept of roll, pitch and yaw angle. Okay? I will strictly recommend you to read few pages from a flight dynamics book by Warren Phillips. Wonderfully it has been written. I will try to give some examples in the forum so that you get better ideas. This is mathematics part of it. Why we are doing all this thing, let us understand. That is more important. We have just seen that if I take two configurations like this, this is the x body axis, z body axis, and of course y, right? Now the gravity force mg will always act downward, which will be in direction of the inertial z axis, right? But as the orientation is changing, its component along x, y, z also will change depending upon what is the angle, elevation angle, what is the azimuth angle, what is the bank angle. So if I want to resolve this component of weight along x, y and z, I need to know how this mg is being resolved using phi, theta and psi, right? And you have seen that we can easily write it as mg x component, I can write it as minus mg sine theta. Similarly, mg y component, I can write it as mg sine phi cos theta, and mg z component, I can write as mg cos phi into cos theta. Okay, clear? So when I write this equation, m u dot minus Vr plus Wq equal to Fgx. For this Fgx I will write minus mg sine theta, then remaining F aerodynamic force x plus F thrust or propulsive force x. Similarly, for other equation also I can write m v dot minus or plus ur minus Wp equal to mg sine phi cos theta plus f ay plus f ty, and other you can easily write using this term. But before we go further, please understand, we have not developed the perturbed equation of motion. We have developed a general equation of motion. But when I was giving you example of mass spring damper system, like mx double dot plus k cx dot plus kx equal to f of t. There the x was measured with reference to the point of equilibrium. So, it was like a short or a small perturbed equation of motion. So, we also need to develop small perturbation equations using these basic equations. That is our aim. We are only trying to understand how these components can be resolved using orientation, using the environmental condition, that is speed, densities, aerodynamic characteristics, propulsive characteristics, and we like to see, if I give a small perturbation, how those forces also change, right. That is why we are developing this. Clear? So, we will be starting with small perturbation. Equation. We will just take one by one equation and try to understand how it is to be developed. Once we understand how to develop, then it becomes very mechanical for you to do. So, I will give one example. Let me take m u dot minus Vr plus Wq is equal to minus mg sin theta plus f ax plus f dx. Please understand, what are all these equations talking about? What are UVW? UVW is the component of total velocity measured with respect to inertial frame, but resolved along local xyz or body fixed xyz direction. Similarly, Q is the pitch rate, R is the yaw rate, and these are the forces along x direction. Okay. Now, once I have to do small perturbation, meaning thereby, when I say small perturbation, I am very clear that once I introduce the perturbation at equilibrium, the perturbation should be so small that it is not going to change the linearity of the whole dynamics. In a sense, if it is the aerodynamic forces which we will be using, assuming a linear model, so by changing the condition about the equilibrium, maybe a cruise in this case, the aerodynamics shall still remain linear. Okay? And under that small perturbation concept, we can use that if I am flying at a steady state condition u1, let us say the cruise, we are introducing disturbances about cruise. So, the plane is cruising, I give a small perturbation and see what is happening to the machine dynamically, right. With this coming back, once the disturbance is withdrawn, what is doing actually. So, one I can write under a small perturbation is, if this is the steady state condition and this is the perturbation introduced small u, then total velocity I can write as sum of this. That is the advantage of small perturbation under the domain of linear approximation, right. Similarly, if I say V, I write V1 plus small v, W, W1 plus small w, right. Similarly, if you see P, I write as P1 plus small p, Q as Q1 plus small q, R, R1 plus small r. So, theta, theta 1 plus small theta, psi, psi 1 plus small psi, phi, phi 1 plus small phi. What are these one? Designated variable, they are the condition at steady state. So, suppose I am flying at a cruise, level cruise like this. Okay. So, at steady state you understand that P1, Q1, R1 all are 0 at steady state if I am going a level cruise, because there are no roll, there are no pitch and there are no yaw at steady state if my equilibrium state is a normal cruise, level unaccelerated cruise. Okay. So, these approximations I will be using. Second thing, on the aerodynamics part, we will say FAX. On the left hand side, I hope you understood what after introducing the perturbation, what is the total velocity u, v, w in their respective axis x, y, z. So, FAX again I will write as FAX1 plus FAX. So, this is the perturbed aerodynamic force along x direction, and FAX1 is the steady state. Similarly, FAY I will write as FAY1 plus FAY, FAZ as FAZ1 plus FAZ. Clear? So, what are FAX, FAY, FAZ? They are the perturbed aerodynamic forces that is introduced because of perturbation given to the airplane at cruise. Clear? This is the total, which is composed of FAX, steady state value, and perturbed value. Naturally, you could see that again everywhere using the concept of advantage which you have by assuming to be linear, small perturbation, result of small perturbation. Okay. Here is a word of caution you must understand. Suppose I am flying such that CL versus alpha follows this train, and you are flying somewhere here. And now if you give a small perturbation, it's made possible that you are going into a nonlinear domain. So there strictly this will not be valid. Okay. But there are ways to handle it. We try to make it quasi-linear. So other many concepts will come, but one is very, very careful once you are applying this. Don't apply this mechanically. Especially today is the era of high angle of attack, high performance aircraft. So mostly you have to be very, very careful how best these assumptions are true when you are applying for dynamic stability analysis. Right? Good morning, friends. Let us solve an example of how to develop perturbed equations of motion. So I will take one equation, that is m u dot plus minus Vr plus Wq is equal to minus mg sine theta plus Fax plus Fpx. Now I will introduce small perturbation. What do? I write m, u dot is u, I write as u1 plus u dot plus for v I will write v1 plus small v, for r I will write r1 plus small r, for w I will write w1 plus small w, then for q I will write q1 plus small q, and on the right hand side I will write minus mg sine theta 1 plus small theta. For fx I will write fa x1 plus fax, and for that ft x1 plus ftx. Please see what we have done. I have taken one equation from the equations of motion, and as we realized that when we did mass spring damper system, we wrote the equation of motion in perturbed quantities, right? Because we measure that x about a displacement about equilibrium. So we are also trying to develop the perturbed equation of motion, and we want to see what is happening if this airplane is disturbed about its equilibrium, about its steady state. U1, V1, R1, whatever one is there, they represent the steady state conditions. So what I have done, for u I have u1 plus u dot, for v, v1 plus v into r is r1 plus r. Similarly, other terms, and we know all this u, v, w, p, q, r, f, ax, ftx, etc. are perturbed quantities. And our focus is to monitor, to check how these variables are changing. Once we give a disturbance, once we withdraw the disturbance, and based on this response, we can comment whether the aircraft is dynamically stable or not. And using this, we try to find out a criteria to be given to a designer so that he can ensure the aircraft is dynamically stable, right? Now here you see, once I am writing this equation like this, we also know that m u dot minus Vr plus Wq is equal to minus mg sine theta plus Fax plus Ftx. So we know that at steady state, what is our steady state for this study? It is the cruise, level unaccelerated cruise. At steady state, that means using our notation, I can write u1 dot minus v1 r1 plus w1 q1 will be automatically equal to mg sine theta 1 plus Fax1 plus Ftx1. So from here you could see that I could easily use that equation with this equation and try to simplify this. Also we need to know what is the expansion of sine A plus B. If I have to just do this, and then I can get a neater equations. Okay. So today what we have seen that what is the meaning of Euler angle, and I will be giving some examples in the forum. We understood the rotation of Euler angles. We also try to understand how should we think in terms of developing perturbed equation of motions by giving a disturbance about steady state, and we will write this equation because finally we want perturbed equation of motions to analyze the dynamic stability of the airplane, and our focus will be monitoring how these quantities are changing. Once we do that, we will be able to develop equation of motions at our own will, and my next lecture will be on how to mathematically proceed. Please understand, we are talking about small perturbation, and then we also will use a concept, the product of two perturbed quantity can be easily neglected, or the perturbed quantity, the perturbed disturbance are so small, we call them small perturbations, and that must satisfy that the product of two perturbed quantities are negligible. We will all use these concepts to develop the equation in a pure mathematical form, which we will be using, right. With that I am ending it here. I don't want to pump in lot many mathematics. So we will be going in a smaller module, you absorb it, again go back, go for next step. Thank you very much.